All right, so let's go ahead and get started. So we're going to talk about existence and uniqueness for solving for solutions for initial value problems. And so this is important, right? So we've been talking about solutions as if if they just existed, right? Solutions may not exist. There may not be any solution at all, right? Um, and it's nice to know if you're looking for something that's not there, right? Um, and so and then uniqueness, if I find that, so in math there's always a question, is there a solution? And if the answer is yes, is that the only solution? So is there a solution is the existence problem? Is there a solution? And uniqueness, is this the only one? Right. um, and so let's just review what we've learned for solving IDP. So for initial value problems, right? So we did analytical techniques in 1.3, 1.4, and 1.5. And these were if it was separable, we did separable equations, we did linear, and we did exact. Okay, so if we have a separable linear exact, we learned an analytical technique, something we could just write down an answer to. Here we did slope fields, or direction fields for a qualitative technique. And then for a numerical technique, we learned Euler's method. And if you recognize for the project, you're going to have to do separable, slope field, and Euler's. Okay. But up to this point, we've assumed that a solution not only exists, but unique. But we're going to address both of these in more rigor. Existence means there is at least one solution. That means there is something out there which solves it. And uniqueness means there's at most one solution. And so if it exists and unique, that means there's exactly one solution. So anything that works that out. So here's the official theorem that can be found on your pages, right? The official theorems are found in your book. And you can go through them, and they are doozies. Let me actually just show it to you real quick. Let's show the doozies, which makes note I'm going to have to crop it out because I can't show the book and post it on YouTube. I do want you to officially look at the big beastie things. All right, so I'm gonna put a little thing. Hi, I am showing book. It's basically, in essence, all you really need to do. Oh, hold on. Hi, YouTube, we're back. In essence, all we need to do is if f, so if I'm given this, right? If I'm given it in kind of implicit form or explicit form, the derivative is some function x and y. If f of x and y, if this function and its derivative with respect to y are continuous, there is a solution and it's unique, right? But there's also something else that is not really nice. This is what my old professor used to tell me all the time when we did stuff. If two solutions are in the same place at the same time, they were the same solution. And that's what it means if something exists and unique. If I find two solutions at the same point at the same time, even if I derive how I get there two different ways, if I derive it one way and I derive it another way, that means those are the exact same solutions. Okay. And we're going to use that theory to allow us to do a lot of really nice things in kind of a hand wavy way that you can quickly get to solutions that you don't have to derive directly. All right, so let's solve. Hold on. This should not be an equal sign. This should be a plus sign. That's a typo. All right. All right, so let's look at this. This is a fairly innocuous this is fairly innocuous in sense of what we have. So let's just solve this. And in fact, since we have some time, now I'll just solve it with you. So here, if we do this, is 1 over plus 1 plus y squared equals dy equals 1 dx. Yeah, someone's mic's not muted.
All the best.
Hit that little mute button right there. Ta-da! It's not the weirdest thing I've heard at all. So here, if we solve this, we're going to get arc tangent of y equals x plus c. That means y equals tangent of x plus c. And here we have y of 0. Y is 0, 0. So here I have 0 equal to tangent of x plus, or 0 plus c. That implies that c is equal to 0. And we have a solution. Y equals to tangent of x. But let me kind of show you something. So here, y equals the tangent of x. And the reason why I want to show you this problem so here's tangent of x, right? But does the solution for here, hold on, I missed terribly. It's bugging me. There you go. So here's tangent of x. But notice once I get to this point, the solution doesn't exist, right? Here the solution stops existing, right? What's the third line say? Arctangent of y equals x plus c. That's an arctan. Sorry. Oh, third line out. Oh, this is here. I'm plugging in 0. My tangent of x plus c. So this is 0 plus c equal to 0. All right, so notice here. Now we do have solutions, right? So note that y squared is continuous on the entire plane, right? On the entire and so is its derivative with respect to y. However, the solutions, they kind of only exist in this area because after this we lose it. But the solution only exists for a small window. And so even if there is a solution, it doesn't mean there is a solution for all time. So here, the solution is only really defined from here to here, because after this, it becomes undefined, right? So here is the solution to my equation. But this solution is only defined when x is between minus and pi over 2 to pi over 2, because once I hit either of these two barriers, my solution doesn't exist. And therefore, anything beyond that doesn't make sense to talk about something. Now, is there something else over here? Sure, right? If I graphed all of tangent, but for this particular solution, this way has no capability of achieving anything else, right? And so it doesn't have the ability to achieve it, and so it falls apart. Okay, and so even if there isn't a solution, it may only exist for some windows. So that's kind of the point of this problem. Okay. All right, let's go to the next page. Third line out. 0 equals. So this is 0 equals tangent of. Oh, yeah. This is x plus c. And then here to solve for c, I'm plugging in my initial condition. 0 equals tangent of 0. So 0 for y equals tangent of 0 for c. Okay. All right. For my friend who messaged me who came late, just remind me at the end of class. Okay. All right, so the next one. All right. So let's do this one. Can I solve this? So solve the initial value problem. So let's solve this initial value problem. So here I'm going to have y prime equals to 3y to the 2/3. Okay. So if I solve this, I have 1 over 3y to the 2/3 dy equals dx. Integrate both sides. Here I get y to the 1/3 equals t plus, this equals x plus c, right? That means y equals x plus c cubed. And here, if I set, now I'm going to use my initial conditions. So 0 equals 0 plus c cubed. That implies c is equal to 0. So here I have y is equal to x cubed. So here's my solution to my equation. And here, if I plug that in, if I take its derivative, is that what I get? Sure, right? 2/3 of this would be x squared, right? Times 3. And so you can just easily plug this in and get that. But is this the only solution? Is this the only solution here? Nope, right? Because there's another solution. I could have y equal to 0. Does that, if y equals to 0, its derivative is y prime is also 0. And is that equal to 3 to the 0 to the 2/3 powers? Yeah, that's true too, right? So what would happen here? Well, 3y to the 2/3 power is continuous everywhere, right? This is continuous everywhere. Continuous everywhere. However, if I take that 3y to the 2/3 dy, if I take that with respect to y, if I take its derivative with, and this, oops, I put total. I should not put total. If I take its partial differentiation with respect to y, not a 2, but the del's. If I take the partial differentiation with respect to y, I get 2y to the minus 1/3. This is not continuous at 0, right? At yeah, right? So at 0, this isn't continuous, right? When I plug in 0 for y, I get it doesn't work, right? So this is no longer continuous, therefore this is not unique. So I guess let me write that's not right. Uniqueness does not hold. That's the more proper way to say uniqueness. Does not hold. Okay, so uniqueness doesn't hold because it's not continuous, right? And so here I have one solution, but here's another solution. Are these solutions both equally viable? Yeah. So which one is your problem? Well, you don't know, right? And so it's real important. So these things tend to come up. All right, let's look at this happy puppy. So yeah, it's nice to know when you have a solution, all this, but if you're working real world problems, you assume you're going to have real world solutions. It's a nice assumption, not always true, right? Well, let me say this is a very likely candidate for an exam question right here. I want you to sketch the solution to the initial value problem of y prime equals y squared to the y squared minus 4 times the sine squared of y cubed plus cosine of y minus 2 divided by 2. And I want you to sketch the solution for this. Let's make it match what I have on my cheat sheet. Go ahead and switch this 2 to a 3 just for kicks. Because this, and the reason I want to do that, this at most can be 1, this at most can be 1. So if I minus 3, I can guarantee something for me. So let's switch that to a 3. All right, so let me ask you a quick question. Does a solution exist? Does a solution exist? And all we have to do is this continuous? Is there any values of y or x that make that uncontinuous? Y can't be 2. Does y being 2 make it continuous? Yeah, so y can't be 2. Well, y of 2 is this equals 0, right? If I graph this mess, let me see if I can graph this mess. See if I can just graph this awful mess. Let's see if I can. Let's see if I can break Desmos. Desmos is soon going to hate me. Soon going to rule the day I lived. It's like, why? Why do you make me graph this awful thing? Okay. So let's just start this thing. Let's just scroll up. Hey, scroll. Here we go. I'm going to say this is y as a function of x. So I'm going to just make this all of x. Just so Desmos doesn't flip out its little brain. And squared x cube minus 3. And I'll just multiply by half. There we go. Yeah, you're fine. Stop it. Stop it. No. Bad Desmos. Oh, I put in a Y. Hi. Yeah, you don't know what to do. Ta-da! It's funny looking, for sure, right? But it is continuous everywhere. So remember, this isn't my function. This is the derivative of my function, right? And it looks like this hot mess, right? This absolute hot mess of an equation. So now, does it exist? Yeah, it's continuous everywhere, right? In fact, from your Calc 1 class, here I have a polynomial multiplied by a trig function addition of trig functions, and therefore this is continuous within its domain. The domain here is everything, so it is continuous, right? If I took this derivative, notice here that it's also, so it's just, yes, if I took the derivative, it's also unique. You day on spelling. And is it unique? And the answer here is yes. Because if I took this derivative, is it going to be some huge product rule? Sure, right? But it's still going to just be a product of polynomials and trig functions, which are all continuous, or sines and cosines, which are all continuous everywhere. And so the answer is yes and yes. So how am I going to do this? Am I going to solve this? Am I going to solve this right here? Can you solve this? I mean, technically it's separable, right? It's all y. But the answer is no. You try to flip that upside down and integrate it, you're going to get a big mess, right? Just an absolute big mess. So what do we know here, though? Do we know some solutions, though? Do you guys know any solutions for this? Any solutions whatsoever? My calculator can. Can your calculator do that? I'm curious if Wolfram Alpha is brave enough to do it. I'm super curious. We're going to test that now. Hello, Wolfram Alpha. Prepare to hate your life. Hi. Yeah, I want to leave the page. Pow. Yeah, I had a feeling you'd do that. You suck. And dy dx is equal to the quantity of y squared minus 4 sine squared y squared, or y cubed, plus cosine y minus 3 divided by 2. Oh, hold on. Yeah. This is a first order now. Thank you for classifying. Alternate forms. Yeah, expanded form. No, solve it. Solve it, you. Yeah, it doesn't. It doesn't solve it for me. It shows me examples, but it doesn't solve it. Wait. The sine wasn't squared? Yeah, sure, the sine squared, right? Sine squared. Fair enough. All right, so what do we do now? Well, do we just, curl up in a ball and cry? Sure, why not? We're students and you got to get used to that at some point. No, do we know any solutions here? And someone put some solutions in, right? Here, is this ever going to be 0? And the answer is no, because I switched this to a 3, right? If I switch this to 3, it's clearly not 0. This can be at most 1. This can be at most 1, but minus 3. This for here will always, always, always be negative, correct? Everyone buy me on that? This is always negative. Can this ever be 0? Sure. Where's this 0 at? Well, at y equals 2 and minus 2, this is 0, right? And so y equals 2 and minus 2, my dy dx is equal to 0. So my slope is 0. What does that mean? It means I'm not changing, right? And that means the solution here at minus 2 and 2 is consistent, right? Now, if this is less than 0, here, no, so here, between 2 and minus 2, I have these two consistent solutions. And notice what I said in the page before. It says if two solutions are ever in the same place at the same time, they are the same solution. Therefore, I can clearly state that any solution, because I'm going to start here, right? That's where I'm starting, right? Any solution here has to be strictly between 2 and -2, right? Because if it ever crossed it, it was this solution because they're at the same point at the same time. So it has no ability to cross whatsoever. So, but also notice something here. This is always negative. This is always negative. This between -2 and 2, this is always going to be negative because that -4 will win, right? And so this is always positive. And so my slope here is positive. And so what has to happen here is I have to have some sort of function which is always positive, which comes real close to these two solutions, but never touches them. And so here I have sketched roughly my solution y, given this initial condition. This is a rough sketch of the solution. Now let me show you in a computer, and then we'll do something else in the computer as well to get you ready for the project. Okay, so here I'm going to use the DE tool thing I showed you before. And it's going to be like, welcome. Hi. Hello. I'm going to type in HVG solver. All right. Yeah, this is fine. From -3 to 3 be perfectly fine. So let's type in this hot garbage. It takes a second to type in, but let's do it anyways. It doesn't recognize that sign. I don't buy it's going to do that correctly. So let me do it this way. And then I'm just going to multiply by 0.05. Yeah, so say show field. Ta-da. So here's our field. Now remember our two solutions that we knew. If it's at 2, and I type in a solution, we get the straight line right here. And if it's at -2, you get another straight line right here. And here, if we start at 0.5, and type in our solution, we get this, which matches exactly what we predicted to do, right? Now, granted, this is using Runge-Cutterford method. And so here we can get a rough sketch of solution. So given any initial value problem that looks like a hot mess, if you can find solutions that are 0 and it's autonomous, you know that the solutions never cross each other. So you can kind of box in your solutions. And then in between those 0 solution or equilibrium, we call this an equilibrium solution since it doesn't change in time. It's always going to be always increasing or always decreasing. And let me explain why real quick. If a solution ever decreased just a little bit, since it's autonomous, the solution right next to it would crash into it. And so that can't happen. And so for autonomous solutions, let me just write down a couple things for you. Autonomous solutions, or for autonomous equations, you're going to have where dy dx is equal to 0, you're going to have what we call equilibrium solutions. And in between those, it's always either increasing or decreasing. Okay. And so given, no matter how crazy this is, for autonomous solution, you're going to find these equilibrium solutions. And in between those, it's always increasing or decreasing. Why? Because we had this. As long as this existence and uniqueness exist, we can make all these nice statements. And so no matter what awful thing I give you, all you have to do is find some equilibrium solutions, and then say, well, is my initial point increasing or decreasing from that? And if it's increasing, you can draw in this solution. If it's decreasing, you just draw in. If it's decreasing, you draw in a solution that looks something like that. Okay. In between them. And then notice here, solutions up here are always going to be decreasing, and they go into like that. And solutions here are always, hold on, let me just draw some more. Let me just, instead of drawing it on my Alpha thing, I have a nice program that does it for me. Hi, nice program. Hi, nice program. And so here, they always will just crash into this line. And if they're below that line, they always just disappear away from that line. Okay. And so you can write in a whole different family of solutions. All right, so let's do the next one real quick. All right, so hi, I'm going to, in fact, this one we're going to do completely in the having machine. Hi. So I want to solve this one, but I'm going to just use numerical methods because that's what life does, right? All right, and then I'm going to switch this from over to Euler's method, right? And I'm going to set my delta t. So here's my delta t, in this case, to 0.5. All right, and I'm going to start with, oops. I need to expand my y. So I need to go from from 10 to minus 10. And the reason I need to do that is I need to make it clear what's going on, right? Because I want to start at y equals 5. So here, I'm going to start at 5 when my solution is 0. Okay. You didn't crash on me. You're supposed to crash on me. I did not crash on me. Oh, fine. Let me extend this out a little bit further. There we go. I got it to break. Let me zoom in from 0 to 7. There we go. All right, so let's look at this solution real quick. Is this really what's happening here? And let me just redraw this real quick on our paper. What do we have here? Here we have, oops, here we have yellow. Why do I have yellow? Here we have blue. I have a solution here at, this is my x, this is my y, and my solution seems to come down at a certain point, and then it just goes crazy, right? And just dives to Nowheresville, right? That's what we see. Goes up and down a lot and just dives and disappears. Now, is that really what's happening here? And let's answer some quick questions. Do solutions exist for this? Do solutions exist? No, I really wanted to put in 5 for this one. Okay. Do solutions exist here? Is this continuous everywhere? Sure, right? This is continuous for x and y, so yeah. So yeah, solutions exist. So the function, here I have a function of x and y. Is this continuous everywhere? Yes. Is the derivative with respect to y continuous everywhere? Yes, right? So I have existence and uniqueness, right? So this is this and unique. Why? Because because f of xy is continuous and del f del y is also continuous. Okay. All right, is there an equilibrium solution here? Is there an EQ solution? Is there an equilibrium solution? The answer is a whole bunch of them, right? When y equals some n pi, right? Whatever n pi is, this is going to be 0, right? It doesn't matter how big this is 0, right? It is 0, therefore it wins. And so here at pi, that's an equilibrium solution. And once it's 0, it's always 0. Here at 0, it's an equilibrium solution. Once it's 0, it's always 0. Here at minus pi, that's an equilibrium solution. So these are nice flat solutions. So notice if we type that into our solver, it shouldn't crash on us. I can't type in pi, so it might actually crash on us. It might actually crash on us. Yeah, it's going to crash anyways. I wish I could type in true pi, but it won't let me. And so here's a nice equilibrium solution. At minus pi is a nice equilibrium solution. So why is the program going silly? What do we call this? What do we call this right here? Does anyone know what we call that? Is this really what's happening? Or is the computer lying to us? And the answer is the computer is lying to us. It doesn't know it is, but it is. And so what we call this right here, this is called a numerical artifact. Okay, this is a numerical artifact. And so the reason why this chapter is so important is because 90% of you are not going to solve differential equations by hand. Let's be honest, right? You're engineers. You're going to type it into what other proprietary software that your company gives you, right? And just crunch through it. However, you'll see things that look like this, and you're going to think, is that really what the problem is doing? And you're going to have to kind of tease out from the equations you put into it and what you did put into it, can this happen? And so what happens here is as we do this method, the Euler method, it starts to break down because you have such small values and the computer can only hold so many values, right? And since there's a truncation, that's why when you do anything with numerics, you always use the double float point, right? As many digits as you can, right? It breaks down and causes the computer algorithm to explode. And so this isn't true, right? So state why Euler's method, and when we type it in the computer, why is it not correct? Because this can never cross. Why is it not correct? If I was going to write that down, because this can never ever cross pi, right? Y equals pi is an equilibrium, is a solution. Is a solution. So y equals pi is a solution for something and existence and uniqueness hold. So no solution can cross it. Okay, so no solution can cross it.